Year 11 homework 6 is about exothermic, endothermic reactions and bond energy calculations. It's another difficult homework. We're setting a lot of difficult homeworks, okay? Because if we can master them in homework, hopefully the exam will be a bit easier. A lot of the questions in the exam are much easier than these. Anyway, first off, it says we've got a reaction here, and we want to know that do the bond energy calculation. We want to work out whether energy is gained or lost in this reaction. Okay, so that's your homework question. So I'm not going to do that, but I'm going to do this one here, this reaction here. H2, hydrogen reaction with bromine to make hydrogen bromide, 2HBr. I'm going to do that one, okay? Now, first thing we have to do with these is calculate how much energy is needed to break bonds. So every part, every chemical reaction always involves breaking bonds first. Doesn't matter whether it's exothermic or endothermic, it involves breaking bonds. So we have to break the reactants bonds. So there's a hydrogen molecule there, an HH molecule. Okay, and there's a bromine molecule as well. So we have to break the hydrogen to hydrogen bond, and we have to break the bromine to bromine bond. All right. Now every bond takes a different amount of energy to break, and we don't need to learn those. They're given for us on these data tables like this. So if ever you get a question like this, you will always be told the energy that's needed to break the bonds. So we just need to find the hydrogen to hydrogen bond, and there it is there. 436 kilojoules per mole. So we can write 436 down there. Okay, now the bromine to bromine bond, let's find that one. There it is there. To break a bromine to bromine bond, it requires 193 kilojoules per mole. So we can write those two down. So if we add those together now, that's the amount of energy needed. That's the amount of energy needed to break all the bonds of the reactants. So 436, 193, that's going to equal, let me think, 629 kilojoules per mole. So that's bond breaking, bond breaking. Now we've done that, let's put a line there. Our next thing is we need to know how much energy is given out when new bonds are made. New bonds are made. So we look at the products, we've got HBr there. Now we don't have one HBr, there's an HBr. We don't have one HBr, we've got two hydrogen bromides. So HBr and HBr. Now, so we now back to our data table. So we don't have one, we have two. Here's our hydrogen bromide bond, 366. So that takes 366. That gives out, I should say, 366 kilojoules per mole for one of them, but we've got two, so we can add another 366. Adding those two together, that's going to equal, once we've added those two together, that's going to equal 732 kilojoules per mole. So that's bond making. Now our final bit is to work out the overall energy transfer. 629 kilojoules per mole to break the bonds, 732 kilojoules per mole given out when new bonds are made. So that is going to be breaking minus making. And that's going to give us the energy transfer, And that's the answer we need, the energy transfer. Okay, so we've got breaking was 629 from there, minus making 732 from there, and that's going to equal minus 103 kilojoules per mole. Now that minus is important because that tells us whether it's endothermic or exothermic. If it's negative, it's exothermic. That energy is given out as heat energy. If it's a positive answer, it's endothermic. Okay, so obviously you're doing a different one, so you will have a different answer. So don't just copy mine. So for my example here, okay, to start with, we started with we just put a line there. I think you could put a line there in yours, to be honest, as well. And we're going to write HH and BR there because they are our reactants. Our reaction path starts with reactants. Okay, and we need to break those bonds. To break those bonds requires energy to be put in, so our energy level diagram is going to go up. And it's going to go up exactly, okay, from there to there. Exactly, that difference there is going to be 629 kilojoules. And that's sometimes called the activation energy, or the energy needed to break all the bonds, bond breaking. Okay, now we've got everything at the top here. Okay, all the atoms at the top are on their own. So I've got my hydrogens, and I've got my bromines, and they're not joined to anything. So notice here they had bonds, whereas here they're on their own. So our next stage is bond making. Now our bond making gives out 732, so we're going to come down now because the energy is given out, so it's lost from the system, so we're going down. Okay, and it goes down a bit further than what we went up, because that was 629. So from here, okay, to here, that difference is going to be 732 kilojoules per mole. So this was bond making. And when we've made all those bonds now, down here we've got our HBr, but we're not one of them, but two of them. Okay. Now the difference between these two levels here, that's the energy transfer, and we work that out to be 103. The difference between those two lines. Okay, so let me recap. That gap there from there is the activation energy, or the energy needed to break all the bonds. It is the same thing. Now your diagram is going to be different because your example is different, okay, but quite similar nonetheless. The activation energy, that was the energy needed to break all the bonds, and we work that out here, breaking 629. 629. Activation energy is the energy needed to break bonds. The energy needed to break bonds. So, difficult question. Let's see how you get on with that. Last question. Also difficult again. We've got to calculate in quantities. What mass of water is needed to make 128 tons of oxygen? Okay, so that is talking about this equation here. So let's write this equation here over on the other page. 2H2O. So 2H2O arrow H2 plus O2. So it's saying what mass of water, so that's going to be the question mark, is needed to make 128 tons of oxygen. 128 tons of oxygen. So that's your question, but I'm not going to do that one. I'm going to do a different one. So the question I'm going to do with you here is around this hydrogen and bromine equation again. So I've got the reaction equation here, H2 plus Br2 arrow 2HBr. My question is what mass of hydrogen, so I'm going to put a question mark on top of the hydrogen, is needed to make 40.5 tons, okay, of hydrogen bromide. And I've got my relative atomic masses there. Hydrogen is 1 and bromine is 80. Now the first thing here is don't get confused by the tons. Tons is just a unit of mass, so we are given a mass of hydrogen bromide. So this is calculating quantities, therefore it's got three stages. First stage is moles, second stage is stoichiometry, okay, and the third stage is moles again. Okay, moles, stoichiometry, moles. These are the three stages. Moles equals mass divided by relative forming mass, or MR. Okay, so the first thing we need to do is work out the formula mass of whatever we've been given the mass of. Now in this case we were given the mass of hydrogen bromide, so that's going to be 40.5 is the mass, and the formula mass, the MR, well I've got one H and one BR in that. That big 2 is a stoichiometry number, so it's not a formula number. Formula numbers are little numbers, and the little number is H1Br1. Okay, so I've got one hydrogen, one bromine, therefore the formula mass is 81. 40.5 divided by 81 is half a mole. Stoichiometry now. Now again, this is a little bit different. Normally, I suppose, in the past, we've often looked at examples where we walk forwards in the equation. Okay, this time we're working backwards, but it's exactly the same. We've got two hydrogen bromides are made from one hydrogen. Okay, so H2 makes 2HBr. Okay, and this time we're told 2 makes 1. So going that way, to get from 2 to 1, okay, there's a 1 there, remember? Okay, to get from 2 to 1, that's divide by 2, that's halving. Okay, it's a halving relationship in my example. Your example might be different, you need to figure it out. Okay, now we don't have 2 moles, we've just calculated we have got half a mole. Okay, so we need to go halving. We divided by 2, we halved. Halving. Okay, so quarter halved is going to be, so half a halved is a quarter, isn't it? So we've got a quarter of a mole in my example. So that now is going to go up to stage 3. Moles equals mass over formula mass. Okay, but we don't want moles, we want to find out what mass of hydrogen. So we need to rearrange this to make mass equals moles times MR. Well, the moles here we've just worked out is going to be a quarter, so we're going to put that quarter in there, multiplied by the formula mass. Well, this time it's the formula mass of the question mark. Well, that's hydrogen H2, so there's 2 hydrogen atoms in that molecule, 1 hydrogen atom is 1, therefore 2 hydrogen atoms is 2, therefore the answer is going to be 0.5. And remember the unit. The unit is whatever the unit was at the start. We started with tons, so it's going to be tons. So that method is identical to the method for that question there. Have a go at your homework.